Okay, the goal in this video is to talk about damped oscillations and damped driven oscillations, which actually relates to these tennis balls, and I'll try and explain how in just a second. Give me just a second to get ready here. Okay, so damped oscillations, I'm going to start by talking about a simple mass spring. We're going to have some equilibrium position here. I should be careful. I should say unstretched position, right? And the oscillation and unstretched, excuse me, the equilibrium and unstretched positions are the same for a horizontal mass spring, not true for vertical. And what we're going to do is we're going to look at the differential equation of motion when we add in some low speed drag, a resistive force that is opposite the velocity's direction and proportional to the speed. So that's what basically the faster you go, the more drag you have, the more air resistance you have. And it's always opposing your motion. If you want to try and write the differential equation in dot, double dot form, etc., you can try that. Pause the video. 1, 2, 3, here I go. Well, I'm going to say that negative kx, the spring force, and then minus bv is equal to ma, and maybe I'll put a v here in blue, where I'm assuming an I hat is implied on here, right? If I stretch this to the right, the force is to the left, negative I hat. I didn't write the I hat. If I'm moving to the right, there should be a drag force to the left. There's a negative I hat. And finally, I'm going to assume that my acceleration is in the positive direction, and then I may get a negative number in the positive I hat. So that's one of the weird quirks about writing this down, is you generally speaking will assume your acceleration is to the right, everything is to the right, v is to the right, and then we get our minus signs here because of their restoring nature. All right, so in this case, I'm going to rewrite that as minus kx minus b x dot equals m x double dot. Now, there's lots of math, and you can see in the workbook from pages 16 to 19, there's lots of math on this. I'm more interested in the result that we find. I'm going to call this omega d, meaning omega damped, is equal to, and I don't want to screw this up, so I'm going to write this down here. It is the square root of omega naught squared minus b over 2m squared for what's called the underdamped case. And I'll show you a visual on that in just a second. But so what's going to happen here is this thing should oscillate and it should die out. And under those conditions where it's oscillating and dying out, we call that underdamped, and this will be the frequency at which it dies out. So B is the damping constant. Notice what happens here. If B is very, very tiny, that's what we mean by underdamped, not much damping. The coefficient in the drag force is low. So if you have a tiny amount of damping, notice it's very close to the resonant frequency that we had before, where omega naught was equal to the square root of k over m. It is a little bit different. Let me go to a simulation now, or well, let's show you a physical example and then a simulation, right? So if I just take one of these tennis balls here, how about this one? If I pull this back, it oscillates, and then the amplitude of oscillation dies out. And we can see that each one of these, it's going to take a little bit different amount of time to die out. But the damping would be like the air resistance on the ball, right? And something about this inverted pendulum, we know that a pendulum is a lot like a spring, and so you could do the math on that. But that's a physical example of a damped pendulum. Again, you pull it back once and just let it rip until it dies out. Okay, the oscillation is damped out. I've got a simulation here. Give me a second. Which one is it? I think it's this. Is this the one I want to use? Yes. Okay, and so here we can see an oscillation with no damping at all right now. I'm going to hit a button in it. So I want you to ignore this term. That's the amplitude of the driver, and we have no driving right now, so we don't have to worry about that. But notice there's no damping coefficient. All right. And so what I'm going to do is I'm going to run this. Let me clear my annotations. Well, one more thing. I want you to watch this plot down in here when I try different amounts of damping. Okay. So give me a second. Let me clear that. Clear this. So let's look at a case with almost no damping. So notice we have a very tiny amount of damping, and we see this thing oscillating, and we see the oscillation is decaying right down in there. Notice B is a tiny number, about 0.1. Okay, so let's clear that out. Now let's see a stronger underdamped case. It's going to reset. So watch the oscillation. 1, 2, 3, go. Notice it only undergoes a couple of oscillations when B is a larger value. So when B is 0.8, right, we see about maybe 2 or 3 oscillations happen. Let's clear that out. And now let's go to what's called critical damping. Ready? It's going to happen quickly. 1, 2, 3, go. Notice it doesn't really complete a full oscillation, right? So that's the amount of damping which causes the oscillation to die out as rapidly as possible. Okay, let me clear that out. Now I'm going to try overdamped. So what this is going to do, I'm going to use more damping than is required to cause this thing to die out as fast as possible. Okay, let's compare this. Here's critical damping, and then I'm going to increase the damping. And it actually takes longer to die out. And now let's go crazy overdamped. That's kind of fun. But so we can see now, I hope this makes a little bit of sense of what this damping coefficient does. Let's just look at them all. If I have almost no damping, we see lots of oscillations. If I have this thing underdamped, but maybe a little bit stronger, we see a couple oscillations. Here's critical damping, the shortest time to get to equilibrium. Here's overdamped, a little bit longer. And if you use way too much damping, it's going to take forever. The drag is fighting it as it's trying to reach equilibrium. So there's a bunch of different cases. Let's stop that screen share. If you want to learn more, read about this. The summary that I care about is on page 19 in volume 3, but there's more. There's a lot of information out there, and the math to solve this differential equation is quite involved, and you can read about that in a differential equations course. I think I did 1 or 2 examples in the book if you really care. All right, now let's move on to damped driven oscillations. So this is very similar. We have all the same terms, but now what we're going to do is we're going to have something over here wiggling so that the spring is forced to oscillate at some different rate omega driver. Notice how many omegas we've got. We've got omega, omega D, omega naught, omega driver. There's so many omegas in this chapter. You got to keep track of them. But what does the force equation look like? It looks like minus kx minus bx double dot. And then we're going to add in a term, some force, I'll call it F naught, sine of omega driver times T equals mx double dot. Now you could debate, wait, should this be plus or minus? And then, well, keep in mind, it's plus and minus because it's oscillating. So it doesn't really matter. We'll just stick a plus on there. So what happens in this case? Let me try and show you this with our example. Which one did I want to go to? I think I want this one. All right, let me go back to a screen share real quick. And so now what I want to do is I'm going to change this A value. All right, and maybe we could change the frequency here. Oh, I forget which one. Did I hit pause? Oh, it's on pause. All right, sorry. Give me just a second. show you what's up. This thing now is going to wiggle back and forth, and it's going to cause the, well, this is the driving force. So there's a driving force. And if I recall, there's a blue line somewhere that you could see. See this blue line in here? That's the equilibrium position of the spring at any point in time. If you're wiggling the end of the spring over time, we expect the equilibrium is going to wiggle back and forth. And now, what are we talking here? On this plot, we're going to look at the cube's position as we wiggle it. All right. And so maybe what I'll do, we'll turn the B to, okay, so let me clear all my crap out. Stop this. So we have no damping right now. B is equal to 0. So this is a driven system. We better put in some damping. And now I'm just going to run this thing. Okay. And we can see that it's trying to reach equilibrium here as it oscillates back and forth. Let's crank this up. Oh, there's a high. And so what will happen here is there's probably some frequency where we're going to get a maximum amplitude. All right, maybe I should lower this down so I can see more amplitude. And let's run this at 10 times speed, just to speed things up a little bit. We could see this kind of settling in. We go faster. And depending on the driver frequency, we get different amplitudes. So notice there's hardly any amplitude now. If I go to a smaller speed, a smaller angular frequency, we should start to see, oh, there's a pretty large oscillation. And if I keep going, it's probably going to get smaller again. And so what am I trying to point out here? After a short period of time, we see the amplitude of the oscillations kind of settle in and reach some equilibrium value. We also saw that somewhere in the middle of here, there's some ideal frequency to drive the system to cause the cube to oscillate as much as possible. If you wiggle it too rapidly, if the driver frequency is too high, then you don't see much oscillation at all. If the driver frequency is too low, like this one, basically the block is sitting almost exactly at equilibrium. It's barely oscillating at all. So there's some ideal frequency. And I think we found that somewhere right around here. Maybe it was right in there, where the amplitude of oscillation starts to get pretty big. We get large oscillations at some special frequency. Let's go to the board and talk about this. All right. And I guess the main things that I want to point out are the following. Let's summarize this. If I make a plot, and I want to use omega driver here, and this is the amplitude of the oscillations, we see that we get a shape that kind of looks like this, where there's some special frequency that causes this thing, and I'm going to try and make this look just right. At some frequency, we get maximum oscillations. Now, it turns out it's not exactly the same as omega naught. Omega naught ends up slightly shifted from the peak, but the peak is approximately omega naught under certain conditions. I'll say it that way. All right. And what do we get here? The position as a function of time ends up obeying this equation. Eventually, it settles in and it matches omega driver. Right? There was a brief kind of chaotic period, and there might be some phase angle involved, but the the position as a function of time eventually settles in and kind of mirrors the oscillation of the driver. Okay, it's kind of like pushing somebody on a swing set. Eventually, they're going to go the same rate you're pushing them if you keep pushing them. Next, we saw The amplitude is given by some complicated function because it gets bigger and smaller. And the function that I've got written down here is F naught divided by, oh my gosh, this is a crazy looking formula. M squared omega driver squared. Whoops. I think I have a typo in my book. So I need to check if this is a squared here as well or not. I guess we could check the units really quick and see. All right, so let's check the units to see if this should be squared or not. But before we do that, I want to point out here, the amplitude, whenever the driving frequency is very close to omega naught, notice the amplitude gets big. So, right, close to omega naught, this term is minimized, and we get the amplitude as large as possible. Let's quick check the units to see if that should be squared or not. If you want to pause the video, you can try and figure it out yourself. Okay, so here, I know that this is kilogram meter per second squared, and mg, right, equals the units of B times meter per second. So in this case, that drops out, that drops out, that drops out, that drops out. So kilograms per second are the units for this letter B. So low speed drag has kilograms per second. The drag constant for some other problem with a V squared would be different. Okay, so now let's see what the units of this term are. We're going to get kilograms per second squared, because that's a B squared, and then I'm going to have radians per second squared. And so in this case, I'm looking at the units of this term. B squared we'll end up with what? B squared omega squared has kilograms squared per seconds to the fourth. And now I can tell, oh crap, I'd better fix that. I forgot a squared right there in the workbook. All right. But so that's damped driven oscillations. I'm talking about this maybe for reasons you can understand. This is important in earthquake physics, right? So you can see there's a natural frequency of, let's say, this one. So if I try and shake this at that frequency, notice I'm driving this oscillator at the right frequency for tennis ball number 2, calling this tennis ball number 2. And when I do that, we see none of the other tennis balls tend to oscillate. So what was that about this frequency? We do see some slight oscillations of the others, but because they're not near the resonance peak, the amplitude of oscillations for the really tall tennis ball and the really short one is somewhere over on this part of the graph. Whereas this tennis ball, I'm driving it at approximately the resonant frequency, and we see a large amplitude oscillation. So that's supposed to be what you learn out of this. I hope that's cool. Let's stop the video.